Yeah, so
Yes, your slides are visible.
okay, yes, thank you. So let me begin by thanking all the organizers for providing me with this opportunity to present this really fascinating piece of computer algebra system called xAct, and it's really amazing as you will see. So yeah, so uh, let me begin by saying that this xAct is essentially for the analytical relativity, essentially, because this conference is themed as numerical analytical relativity. xAct is efficient at doing the analytical relativity part. Okay, so yeah, excellent. So here is a plan of my talk. So first I'll introduce xAct, and then I'll tell, then I'll give some sample abstract computations using extensor, a package within xAct. Then we'll see some. Then we'll do a component computation using xcoba. Sorry, it's not written here. And then finally we'll see some sample computations using expert and xtrans. Okay, so let's move on. Yeah, so what is the aim of this lecture? So xAct is a huge collection of many packages that can do a variety of problems. This talk by no means provide any justification to the vast amount of things that can be coded using xAct. The aim of this talk is to give a flavor of various things that xAct can do that are related to the problems in general relativity. The idea is to introduce people who are very new to or never seen xAct, what xAct can do, and possibly introducing in such a way that they may use it for their own research to fasten their research. Aim of the next lecture, which is the main lecture, is to give a methodology of how to use this xAct to code the boundary Sachs formalism that Professor Amitabh Virmani introduced in the morning session. So the basic hurdle, as was pointed out in Professor Virmani's lecture, is covariance, the issue of covariance, because the full spacetime is four-dimensional, and we are restricted to two-dimensional indices, for example. So there is a lack of full covariance. So the idea is how do we make how do we code this partial covariance in Excel? The idea will be to essentially respect the covariance with respect to the sphere metric and not the full four-dimensional metric. And this is a challenge: how to make xAct deal with such partial covariance. Okay, so it's not changing. Yeah. Sorry, I'm not able to change the slides. Okay, yeah. Yeah, so just a second. Yeah, so what is xAct? xAct is essentially a collection of hierarchical Mathematica package, which are written in Wolfram language. And that is, there are 24 such packages. The purpose of this talk is to show the utility of this package for a variety of problems in general relativity. It performs both abstract computations and component computations, and possibly mixed ones also. Here we shall assume very basic familiarity with Mathematica. One more point is that the utility of this xAct goes well beyond general relativity, and it can be used to field theory calculations, for example, by using the package called field6, which can, in principle, handle spinors, gamma matrices, etc., etc. And how useful is xAct is can be seen by that there are 1,000+ publications already, and weightage of how much of it goes to GRQC is roughly 47%, and 40% of that goes to high energy physics theory, 8% to astrophysics, and 5% to other areas. And finally, there are 1100 plus authors that have made use of xAct. Yeah, so here are the resources. Here is a list of resources. You can go to the xAct web page where you can find all information related to download, installation, documentation, which provides various tutorials, citations of the various papers which cite xAct, frequently asked questions, and so on and so forth. There is an xAct forum where you can post your questions if you're stuck, and then the experts will reply to your queries. And finally, there is a Mathematica Stack Exchange also, where you can post your questions and get some answers. Here is a very brief review of how do you go about installation. From xAct web page, you go to download section and download the compressed xAct file. And the xAct uncompress the file and place it in the directory where your Mathematica installation is done. For example, for the system on this computer that I'm using, it's placed in the C directory under program files, full from research, Mathematica 12, add-ons, applications, and finally this xAct 1.2.2. So to run xAct, open Mathematica and first run the following command. That is set directory, and here you set the name of your directory where xAct is located. For example, for this system, we use this command, and to run any package, we use the standard Mathematica command. This one, like this one. Okay, so this thing loads the extensor package. We will see this example very soon. Okay, so xAct, once again, let me stress again, it's a hierarchical collection of Mathematica package. And when a package is loaded, all packages it requires are automatically loaded. In all, there are about 1500 xAct symbols, 450 of which are just in extensor alone. And this is the one which we will use today and tomorrow also, mostly. And extensor is a very major package, and that we shall see soon. Here are the main categories of the packages, core packages. This is xcore, xperm, extensor, and xgoba. Xcore is like administrative kind of package which manages all other packages. Xperm is where the permutation theory and group theory, etc., are coded. Extensor is the one which is for the tensor computations. Xgoba is for when we restrict to particular coordinate system and do component computations. Then there are application packages, for example, expert, which one can use to do metric perturbation theory. Harmonics, where we deal with tensor special harmonic. Spinners, for obviously dealing with spinners. Extras for doing field theory. Field sex, which deals with fermions, H fields, BRST cohomology, and so on and so forth. Finally, there are certain input and output packages. xAct, this is for formatting your expressions to take out of Mathematica in nice LaTeX form. And similarly, xprint for graphical interface to xAct. Okay, so yeah, so let's start with doing some computations. And let's start with setting up the directory. And then we load this package called tensor. So it shows that it is loaded. And yeah, okay. Yeah, so notice how the xperm package here is automatically loaded because xtensor requires that. In xAct, we need to predefine everything. Every symbol has to have a meaning, and that meaning is given by the user. So the first thing that we define is the manifold itself. So here is how we define a manifold. So def manifold, and as in Mathematica, everything is in square brackets, all the inputs. M is the name of the manifold. 4 is the dimension of the manifold, and these indices are for the for labeling the indices of the various tensors that we shall define. And yes, so let's define some tensor field on this manifold M. So the idea is to use this command def tensor phi and this square bracket without any argument. This means that it does not have any tensor index, and this object depends on the manifold M. So let's run it. So see, it has become black, and it means that this object, this scalar tensor field, has been defined. Next, we define a vector. So vector V, which will have index A and which will be on manifold M. Notice here that this vector is a contravariant vector, and this we know because there is no minus here, V of A. Like for example, if you see this tensor F, so whenever there is a minus sign, that means the index will be lower, and whenever there is no minus sign, the index will be up. So that's how we define. So this vector field now V of A has been defined. Let's now define a tensor field which is antisymmetric in its indices. So this field is F, antisymmetric in A and B indices, and these are lower indices because we have put the minus sign explicitly. And this object is defined on the manifold M. So we do that, and okay. So now since we have defined, let's see. So if we enter V of A, what we find is that the index A goes up. Similarly, when we input V of minus A, then the entry is down, and we have a covariant vector. The second rank tensor that we defined was a covariant second rank tensor, and this is what it is. So it shows down. Okay, so note that A means a contravariant or upper index, while minus A means a covariant or lower index. Next, we define a metric on the four-dimensional manifold. So for this, there is a command called def metric. The first entry, which is -1, is essentially giving the sign of the determinant of the metric. Second entry is defining the metric field for us, and we are defining it in the covariant form. And the final entry, CD, is the symbol for the covariant derivative. So let's run it. So once we do that, xAct goes on defining various things. Okay, so having defined the metric tensor, let's move on. Just a minute. Yeah. So yeah, so -1 denotes the determinant of the metric. CD is the covariant derivative associated with this metric. And contractions with the Kronecker delta tensor are automatic. For example, Kronecker delta is entered like this. So this has a lower index and an upper index. So suppose we take V of A and then contract it with this delta. So you see what has happened. The Einstein summation convention is already taken into account, and because it is delta, the index B is raised. The Leibniz rule is automatic. For example, suppose I define a quantity Ex, which is essentially product of this F and B, which you can see here, F, B, C, B, C. Then, and recall, the way to define a covariant derivative is you first do this CD. This was the symbol that we will use for covariant derivative. This means covariant derivative along A direction, and then in this square bracket we put the expression of which we want covariant derivative. So you see what has happened is, so this essentially is covariant derivative is acting on product of these two guys, and Leibniz rule tells that the covariant derivative has to act on F first, and then on a second term on V. So here are these two terms. So it is acting on F, and the covariant derivative is acting on V. Okay, so next let's introduce a very important command called toCanonical. This is, in my opinion, one of the most important of the commands. So let's define a quantity called Ex1. which is essentially the earlier quantity Ex, which was product of FBC and BC with VB. So now you see what is happening is this is an antisymmetric object, and we are multiplying with two vectors. And you see what two canonical does. So it's like these are symmetric in B and C, antisymmetric in B and C. So obviously the answer should 0, and which is what xAct is giving us. So two canonical is one of the most powerful command for simplifying expression. It puts the indices in order based on symmetry properties and rearranges the terms and indices in a suitable order. Okay, finally, let's see how xAct remembers how you originally defined an object. For example, if remember we defined V as a contravariant tensor, and okay, so I'll explain what these dollars are. So suppose this is separate metric. Separate metric means just strip off any raising or lowering has been done using a metric. For example, this vector we originally was defined as a contravariant vector, but here I have entered it as a covariant vector. So obviously, to lower the index, I'll have to introduce some metric, and that metric was G, which we defined. So that's what separate metric does. Now you see these funny looking indices. So this let's remove these dollar indices, and this we do is there is a command for doing so that's called screen dollar indices. So once we do that, you see very neatly what this object is: G, BA, BB. Okay, so yeah, more or less this xAct follows Walt's conventions for signs, Riemann indices order, etc., etc. For spinners, it follows spinners and spacetime by Penrose and Brindler, and the sign configuration for variables are kept as in Walt's book by default. They may be changed at the beginning of a session by this dollar. For example, acceleration sign, what it is, you can change it to -1. Epsilon tensor sign, it can be -1 or +1, whatever you want, so on and so forth. Okay, so let's move on. So having just learned how to define various quantities, we move on further. Okay, now let's do some abstract computations with extensors. Once again, okay. Just a minute. Let me go back. I have to clear some things. Yeah. Okay. Before that, let's see a little bit of xCOBA. Yeah. So xCOBA is when we restrict our computation to a particular chart. So xco means coordinate, BA basis. So let's load xCOBA. Then what we define is we define a basis for the tangent of the manifold. So here is how we do it. So there is a basis called B, where this basis is on the tangent manifold of M, and the labels that we shall use. This is a 4-dimensional manifold, and we'll use the labels 0, 1, 2, 3 for labeling the indices. Okay, so yeah. So now how do we define tensors in xCOBA? So we define these tensors will be called C tensors. C means coordinate tensors. So for example, they are entered as some lists. So A, for example, okay, let me, yeah. So you see, this is entered as a list. So it's the antisymmetric tensor. Anyways, never bother. Let's. It's a it's a 2 cross 2 matrix essentially, which we'll see below. And then let's define W. with B. So notice here, first we have entered all the components that we want, and then we specify that it is covariant or contravariant by making in the last two entries whether it is plus B or minus B. So here it is minus B and minus B, which means it's a covariant second rank tensor. Similarly, this W, which is essentially a vector with entries 7, 8, 9, 10, and it's without minus B, so it's a up index and a contravariant vector. So let's see. So when we enter W of B, you see how it is representing it. It's representing it as a column, and B is just above, representing that it's a contravariant vector. Similarly, for A, we have two down indices, and these are the entries that I mentioned: 0, 1, 2, 3, -1, and it's an antisymmetric. Okay, let's define this quantity. Let's multiply A with WB. You see what it has done? It has essentially multiplied this matrix with this vector and given another vector. And notice that it was a contravariant second rank tensor. And W is a covariant contravariant vector. So obviously the result will be a covariant vector, and that's what we are getting. Now let's multiply this EX2 with another W. Now WB is symmetric and A is antisymmetric. Obviously we should get result 0, and that's what we get. Now traditionally the abstract and component computations are very different, and they are done separately. What xAct does is provides a framework where they can be performed in a coherent manner. To see this example, let's take an example of this. So let's define FAB that we had defined earlier in the X tensor, and A minus B is in the X coba. So if we do that, it doesn't do anything essentially. Okay, so now what we do is okay, this is nothing. Just forget it. Okay, it does nothing yet. So next, what we do is we define a tensor G in which is symmetric in A and B indices and defined on the manifold M. And now what we do is we define a quantity GAB and AAB. Of this W minus A and WA, this is like a scalar. And once we ask it to expand, so it does that. But here it assumes that there is some metric, okay, which we have not yet defined. In the basis, the basis has not been specified for the metric, so it just gives them in component form. Now we can go to actual metric by changing this metric to a diagonal matrix -1, 1, 1. This is like a Minkowski metric, and it's in the both down indices. And once we do that, we get the answer. Okay, so having done this session, so let's remove all the definitions, and let's undefine all the tensors that we have defined. Let's undefine all the bases we defined. Let's undefine the manifolds, and let's remove the vectors that we did. So there are no symbols left for user to. Okay, so with this, we have just demonstrated a little of X tensor and X coba. Now we will move on to abstract computation with X tensor in a little more detail, which is more suitable for general intuitive. So are there any questions at this point?
I have one more small question.
Yeah.
Yeah, so the two canonical, what is
Mhm.
that command exactly doing? Like, is it just simplifying the expression and just rearranging
Yeah,
the indices?
yeah. So two canonical essentially, for example, suppose okay, let's do it right away. Let me give an example here only. Okay, I'll give the example and then we'll see. Okay, let me do it right
Sure,
away. Just
sure.
yeah. So let's define the manifold again. Yeah. Okay, I think it already knows that it is there. Yeah. So let's see. So let's take an example. Let's say ex10 equal to met minus b minus a. So you see in this, what is happening is b index is first and a index is second. So what two canonical does, for example, is it will rearrange the indices in a lexicographic setting. That is, a should come first, b should come second. Okay. So and it let's see what has happened. It has exchanged the indices. Even though I had entered it as b and a, now it has made it a and b without any sign because it knows that metric is a symmetric tensor. So this is one example. Two canonical further, suppose it was an antisymmetric tensor, then what it will do is it will put a minus sign and rearrange the indices. Other than this, there it also raises and lowers the indices on the tensors, but that is only to be done in very specific settings when you have like metric compatible covariant derivatives. So as we'll see in the next lecture tomorrow, we do not want that feature of two canonical because it can make some crazy kind of rearrangements which we do not want and which is actually wrong. So and actually xAct points out as it gives a warning that there is a metric not a metric incompatible covariant derivative in the process of using two canonical. So that's yeah. So this is what
Yeah.
two canonical does, and it also shuffles the terms. Like some terms will come first and others will go later, like that. Okay.
So and so I think so I just encountered a difficulty a few times there. So while you use partial derivatives, okay, then also raising and lowering creates a problem there.
Yeah, yeah, exactly. So for that, I'll tell tomorrow how to deal with that. Essentially, you have to. There are various options for two canonical. So you have to tell xAct that it should not do that operation. I'll tell that in tomorrow's lecture because that is what the problem will be. Okay.
Okay, and there's another question from Shovik Shen. So what were the dollar indices that were screened? So he's asking what the screening of the dollar indices.
Hello.
Hello. So yeah, there's a question from Shovik. So what were the dollar indices that were screened?
Oh yeah. So see, the point is whenever there are dummy indices, so when you do some computation, there are a lot of steps that are done, and so the dollar indices. See, once we define, for example, the manifold, so there are finite number of indices we have put in Mathematica. Okay. Now it can happen that we have taken a product of lot of tensors. Okay, and then eventually it will run out of indices. So what it does is it takes one of the indices and attaches dummy, dollar indices to that. Okay, and then it will like be essentially dollar 1 2 3 whatever to n number of them. Okay, virtually it is like limited to the capacity of your computer that yeah, so the dollar indices are for Mathematica's internal purpose when it runs out of the indices, which it can relabel as dummy indices. So is that fine?
I think that's fine.
Okay, yeah.
Also just
I have one. Excuse me.
Yeah, sure.
Okay, so suppose I want to include torsion, let's say,
Yeah.
on the grad. So what should I do in that case?
Yeah. Torsion case will come. I mean, it's a few slides down the line. Okay, so I'll tell you what to do. Okay.
Sure.
Yeah.
Okay, and just one more small thing,
Mhm.
Kashyap sir. So when you are like in this particular slide, when you are defining the manifold, the GI, JKL, those are still in blue. So I
Oh,
think
sorry. I think what has happened is some of the variables did not clear up.
yeah.
So yeah. So maybe I can restart this and then it will go. Okay, let me do that. Just yeah. So let me redo this. With kernel. Yeah. Sorry, excuse me. Just give me some minutes. Okay. Let's yeah. No, I think should be fine. Yeah. So now things are fine. Okay. Yeah. So let's proceed. So we define the metric is lower, and see how Mathematica sees it. It's in the way Mathematica deals with this, and the way it shows to us is this. And similarly, the met AB is GAB, and the metric minus AB is essentially canonical delta. Now, we know that metric has its covariant derivative 0. So this is what happens if you apply the metric. So this is as usual. Next, let's see how to enter the Riemann curvature. Okay, Riemann tensor. So Riemann tensor has 4 indices. In Wald's notation, the fourth index is up and the first 3 are down. So if we enter it, so Riemann CD is with respect to the covariant derivative that we have defined. And you see, so this is telling with respect to the covariant derivative, and these are the index placement. Similarly, for Ricci scalar, with both down indices, we have entered it like this. And then for the Ricci scalar, where there are no indices, it is entered like this. And you see, we do get Riemann Ricci scalar by contracting 2 of the indices. For example, if you contract the second index and the fourth index, this is down, this is up, we get the Ricci tensor. And similarly, Ricci scalar is obtained from Ricci tensor by contracting the indices. That's what it gives.
There is one question.
Yeah.
Sorry.
Yeah, sure.
So there is one question from Sanket Thakkar. He is asking that how we calculate the Christoffel symbols.
How do we calculate? Yeah. I'll explain. It's just coming. Okay, there's a simple command. How to do it? Okay. Yeah. So now you see, let's use xAct to verify some complicated things. But before that, xAct is already aware of various symmetry properties that the Riemann tensor has. For example, if you see this expression, so yeah, let's just see this expression. So this is RABCD and RBACD. So here we exchange the first 2 indices and added them up. We know that this is antisymmetric in first 2 indices, so this must add to 0. So that's where 2 canonical comes. So this percentage is for whatever the last output was to act on that. And that's what you see. If we do 2 canonical, it essentially gives you. Similarly, if we see that there is a reflection symmetry, like if you have a Riemann tensor with ABCD and just reverse them, DCBA, and subtract, this also must be 0. This is property of a Riemann tensor, and that's what we. Okay, so now comes the torsion. So yeah, so there is a command for torsion, and torsion with respect to this metric. This metric is 0 essentially. So by default, torsion is 0. We'll see how to introduce torsion shortly. Okay, so this is so far. Yeah, so now Christoffels will come. Okay, so as the question was asked, let's define the Riemann CD. So now this percentage means the previous expression. Let's convert Riemann to Christoffel. So there is this command. Now once again you notice these because it has run out of such indices, so it will assign these dollar indices, and these will be unique throughout the computation. Okay, for example, this index B1 $2972 is here, 2972, etc., etc. But this is not good for us. Maybe it's good for the machine, but not for us. So we can get rid of them by using the command screen dollar indices. So now you see the same expression looks much cleaner for us. And in fact, we can, instead of doing it again and again, we can do it permanently by defining this global command called preprint screen dollar indices. Once we do that, for rest of the program, we don't have to worry about that. So you see, Riemann tensor has Riemann to Christoffel does not produce any dollar indices. But as how does Mathematica deal with it? It essentially still uses those dollar indices, but that's for it to worry about. Okay. Now, so here's the idea. So there is this Riemann CD, ABCD, and then we convert Riemann to Christoffel, and then Christoffel to metric. So let's do it in 2 steps actually. So you see what has happened is, so it has converted Riemann to the Christoffel connections, and then we convert Christoffel to metric. So you see, Riemann tensor has been re-expressed in terms of the metric and its derivatives. Okay, so now this brute force expression is very helpful in proving various identities. Let's take example of first Bianchi identity. Let's prove it. So what is first Bianchi identity? What it says is you just take the Riemann tensor and add, cyclically permute the first 3 indices and add them up. And so that's what we do. So this must be 0. Okay, let's see how to do that. So what we will do is we will take this Bianchi one, first convert Riemann to Christoffel and Christoffel to metric. Let's do that. So it already did that. And then we ask to canonical. And it adds all of them and it's 0. So you see the magic of this to canonical command. Now let's do the second Bianchi identity. Yeah. So second Bianchi identity is essentially you take the covariant derivative of the Riemann tensor and then antisymmetrize in the first 3 indices, including the covariant derivative. So this is covariant derivative with A, B, C, Riemann, B, C, D, E. So you antisymmetrize in A, B, C. That's how we tell it. And once we do that, so this is the expression, antisymmetrized form of the expression. Once again, we do the standard thing, convert this covariant derivative to Christoffel. So once we do that, it does that. Then there are a lot of Riemann tensors. We convert them to Christoffel. And then we convert Christoffel to metric. It might take a bit, takes a few seconds. So let it run. Yeah, so now you see it's so huge expression that it's not even showing all of them. But then once we ask it to canonicalize, it's still running. So it's basically canceling all the terms wherever positives and that's it. So it gives the result 0. So this is how you go about proving certain identities which are there. Yeah. So working with torsion tensor, as someone asked. So in xAct, there is a possibility of defining multiple covariant derivatives, not just one. So let's define another covariant derivative, but this time this has torsion. Okay. So def cov d is the defined covariant derivative, and the name that we will give is CDT, covariant derivative with torsion, CD with torsion, and it will have a lower index And torsion true means it will have non-zero torsion. And symbol of the covariant derivative is will be this colon and or the curly D. Okay, let's do that. So once we shift enter, it's giving us, I mean, it's telling us what it has already defined. So now, here is the list of things associated with this covariant derivative. There is this torsion associated with this curly D. There is this Christoffel curve associated with curly D. Riemann associated with this curly D, and the Ricci scale tensor associated with this curly D. Okay, so now the fact that there is a torsion means that the commutation of covariant derivatives now gives an additional term. Let's see how. So for this, let's define a tensor or the vector field VA on the manifold M. So now see, this is how we take the covariant. Another way of acting covariant derivative is first you take this vector field V, then you act on it with the covariant derivative CD. This is the original covariant derivative that we had, okay, not the curly D. This is Nabla one, okay. So and then you act with covariant derivative A, and then there is a command called sort covariant derivatives, which essentially shuffles commutes the covariant derivatives if it has to. So we defined grad A, grad B, VC. So it has converted it to grad B, grad C, but with the additional Riemann tensor that all of us familiar with. So there is so this is the result. Now, but if we repeat the same exercise, but this time with CDT, the other covariant derivative with torsion. See what is happening. Yeah. So you see, we get the same thing. This Riemann, then the I mean the sorted covariant derivatives, but then there is this additional torsion. So yeah, so that's it. There is another way of arriving at the same, and that is through commute derivatives. Suppose we define this quantity dA dB, curly dA, curly dB, VC. So then in this past expression, what we'll say is commute the covariant derivatives. That is, instead of order AB, keep the order BA. If we do that, we once again get the same expression that we got. So that's it. So now, similarly, how much time do we have? Hello.
Yeah, I will just check.
Okay.
So it's 3:45 now. So I think the session ends at around. Let me just.
Yeah, you have 15 more minutes.
Okay, yeah. So let's speed up a little. So now, so you see, we know how to deal with covariant derivatives which have non-zero torsions. So once again, we can go on proving certain identities involving this torsion tensor. So for example, let's something called the second Bianchi identity. Here, what we have to do is there is this Riemann tensor and the torsion. And then once we have this product, we have to anti-symmetrize in the A, B, C indices, C, B, and A, B, and C. So let's define this first, and then anti-symmetrize. Now the idea is very simple. What we'll do is we'll again convert covariant derivative to Christoffel. Then there will be Riemann tensors to Christoffel, then torsion to Christoffel, and etc. etc. So with this, hopefully it's still running, and eventually it's showing all the result, but eventually we find that the identity indeed is satisfied. Similarly, we can check for the first Bianchi identities, but let's keep it for another day. Yeah. So now for the further session, let's define some of the things. Undefine metric, undefine UDT, undefine tensor. I think everything is done. And let's move on. Other things that X tensor can do. So we can work with different metrics at the same time, but only the metric that we define for the first time will raise or lower indices. We'll see an example to work. In particular, it is possible to work with conformally related matrices. We can work also with product of matrices when they are diagonal, but only when they are diagonal. We can work with Einstein and Wild tensors, work with the epsilon tensors, take Lie derivatives, do variational derivatives. This we will see perhaps towards the end of this session. And then there are products other than, okay, what is this? There are so many other things that can be done. Okay, let's go on. Yeah, so now let's do some component computation. Here we will load the package xCoba. Yeah, so here, how do we go about doing this? So here first we have to define a chart. And the name of the chart is SCHW Schwarzschild on the metric M. The indices that will denote is 0, 1, 2, 3. And there will be this coordinates T, R, theta, phi. All of these are taken as scalar fields. And then there is this chart. We can give the chart a color. Let's call it blue. Blue will be the color. And so on and so forth. So once we do that, and also let's define something called mass, a constant symbol, and we have to print it as A. So that's what we do. And then we define a C tensor, which is a diagonal matrix, and which we call MET, and MET AB is essentially this. So now all of us can recognize this as a Schwarzschild metric. And here is a funny thing which I noticed, and I don't have an explanation for that. When we ask it to basis expand this metric in Schwarzschild coordinates, this gives a standard form that dr squared upon 1 minus 2rm plus dt squared minus 1 plus this thing. But notice that it somehow gives these indices extra. I don't know why. So this I do not know. So, but anyways, keeping that thing in mind, this is the standard form in which you write metric in the textbooks or in papers. Okay. So now, so far, we have not declared that this MET is a C tensor, but we have not told xAct or xCoba that this is a metric. So what is going to happen, for example, is if I do MET AB, because it is naturally defined as minus A minus B, but if it is up, then it's telling that metric on V bundle, there is no metric that has been defined. Okay. So, but what we can do nonetheless is manually define inverse of metric, and then it will give us, this is the inverse. See, it has become cosine squared theta. Okay, let's now define contravariant vector in the coordinate basis. So these are its components, and this swash means it is upper index, or when we enter it like this, we see that it is upper index 0 r equal to 0. The above is a contravariant because we use swash rather than minus 1, and but we can manually do that by multiplying this matrix that we had defined, and it does the job. Yeah, so okay, so there is a way in which we can set the metric. So this MET object that we have defined, we can declare to Mathematica or xAct that it's a metric, and the command is the following. So set coordinate metric MET in the Schwarzschild coordinates, and its signature is that it has 3 plus signs, 1 minus sign, and 0 zeros. So once we do that, now it will recognize that MET is indeed a metric. And so you see what is happening. Earlier it was complaining that there is no metric. So it was not giving the answer for this, but now it is doing that. Okay. So similarly, we can do a contraction, we can get a scalar. And this time, this MET minus A essentially is identity. And the inverse metric, all of it is taking now. Okay. So,
sorry, Sitender, just one quick question.
yeah.
I mean,
Are there methods for tetrad?
Yeah.
If you convert the basis to an orthonormal basis, then what happens? Let's say for Schwarzschild.
Yeah, they are there. I mean, so it can do that. So
do you have any one example or no?
Right now, not in this talk, but if you want, I can give tomorrow.
Okay.
Yeah,
that's fine. Thanks.
Okay. Yeah. So now once again we can define the covariant derivative, and covariant, the way to define is covariant derivative of metric and with respect to met, and the symbol that we'll use for that is CD. And once we do that, CD, the covariant derivative of the vector VB, because this is a vector, this is covariant derivative, it's a tensor, second rank tensor, and that's what it is giving. This was up, this was down, so you see this is up, this is down, and this is the covariant derivative of that. And covariant derivative of a metric is obviously 0, and that's what it is giving. Now, there is a way to, once again, given, we can calculate the Christoffel connection, and that's how it is giving. Let's put it in the component form. So that's how it is giving. And yeah, so see what is happening here is, okay, let me try to explain a little. If you can see, there are various vectors. It's a collection of vectors. So how it is doing is, the first index, take the first index, and then take the second index. See, for example, this is 1, 1, 1, 1, 1, 2. So take the first two indices, make it as a matrix, and in the third index, create a vector. So for example, this entry, this whole thing is 1, 1, and then the first index is 1, 2, 3, 4. So this is one vector which is formed out of 1, 2, first two indices. Then this is second entry, 1, 2 of that thing, and then it will run to 4. Okay, so this is how it arranges. Okay, so yeah, so lack of time, but it's simple. If you stare at it, you will get to know how it is arranging the thing. Now in the basis, it will put the usual thing that we have. Okay, so yeah, now let's see how to
there is one question in the chat box.
Yeah,
does xAct follow Wall's book for notations and all?
Yeah. Yes.
Okay.
Yes, it does. Yeah.
And one more question is that can we find killing vectors of the metric? From Sanket Thakur.
I see. Okay, this I have not used, but I think there must be. There must be. This is my guess, but it must be. I'll find out and give the answer tomorrow. Okay. Yeah. Okay. So once again, let's see. Let's do this. Let's commute the covariant derivatives and see the differences. So it very simply does this. But is this equal to the answer that we want? So the answer, we know that the difference, I mean, commutation of a covariant derivative on a vector is essentially proportional to Riemann tensor, as we are already seen. So here, in another way of doing that, this object we calculated, and we want it to be equal to Riemann CD times V, and there is this double equality, which means it has to test whether this thing is equal or not. So once we do that, and once we ask, it is trying to check whether these two things are equal or not. We ask it to simplify, and it says true. So once again, we see that it is doing the job, and the torsion essentially is 0. Further, the Ricci of Schwarzschild metric is tensor is 0. And once again, we can calculate the Riemann tensor. It's a very nice arrangement, but I think there's not much time to explain this. So these are the Riemann tensor components. To proceed further, let's undefine various things. Okay, set. Right. Okay. Yeah, so there are various coordinates in which you can do this. So let's Kerr-Neumann in Boyer link with set coordinates. There's no time for this. Kerr-Neumann in rotating frame. I mean, there are tutorials on this.